So, welcome everybody. Uh, Today we are going to solve the IFA 2020's problem number 10. Now, this problem practically deals with a very uh, simple, let's say, geometrical observation. So as you can see, this problem is telling us that for which of these following statements are true. Like for every connected subset Y of a metric space X, then its interior is connected always. And for every connected subset Y of a metric space, the boundary of it is always connected. Now, as you know that uh, the definitions of connectedness is when it is not disconnected. So when is a subset of a metric space disconnected? When it can be written as disjoint union of two open subsets of that metric space. Now, the fact is that in this problem, particularly, in this problem, 2 is automatically false. It is automatically false. What's the reason? It is automatically false because of this reason that suppose you take your X to be the metric space R under the normal Euclidean metric. Okay. So this is the normal Euclidean metric. That is this mod of B comma A. It means B minus A. Mod of B minus A. Okay. So normal Euclidean metric. And in that, if you take a closed interval a comma b, then any closed interval a comma b is always connected in R. So this is always connected, even it is path connected, you can say, in R, right? So let's say I call this as my y. So now if I take the boundary of this y, that is the del y, this is what? This is just singleton E and this is just collection of singleton points, right? So A and B. Now, then in this real line, this is just distinct 2 points, A and B. So that's the del y. And of course, from here you can directly conclude that even if a subset of the metric space is connected, its boundary might not be connected. All right. So that's second problem. That's why the second statement is always false because the boundary is just a comma b, that and they do not have any connectedness. All right. Okay. Fine. So the first one is a little bit trickier. So the first one says is that it's kind of there we for the second one we had the boundary, now we have the interior. All right. So suppose you take this. So D2 is a standard two-dimensional disk. All right. So D2 is a standard two-dimensional disk. So if I take this D2 wedge D2, so what does that mean geometrically? It means that uh, in R2, what we are actually taking is that we are taking two unit disks which are connected through a single point. All right. So there is this connection. So since these are, so let's just say D21 and D22. Right. So uh, uh, if I take these type of two disks in R2, then the wedge means that two disks are actually connected at a single point. That means they have a tangent common at a single point. That's precisely what it means. Now, if you look at the interior of, now this is, so if I take this as my y, then y is path connected, right? Because the reason is that if whatever points you take, so see D12 or D22, both of them are path connected individually, correct? Because these are disks. Now, since they have a point common, hence hence D1 to wedge D2 to, it also becomes path connected because of this phenomenon. Like if you take this and connected at a point, then there's no problem whenever we are dealing with points in D1 or points in D2, right? There are no problem. But the only problem is when I have to go from D1 to D2 to, right? But here it is simplified because since I have a point common, I can always go via this point to here. Hence, it is always path connected. But the moment you take but the moment you take the interior, but the moment you take the interior of these this set, the moment you take y interior, what does it mean? So y interior now becomes disjoint union of two open subsets. Why is that? The reason behind is that if you take the interior, then the interior looks like this. All right. Now, since the boundary is omitted, the point that was holding these two things together, this point, let's say P0, it's omitted from the boundary. All right. So now the interior of the interior of your y is practically the interior of this union interior of this. But since the only thing that they had in common was a point in their common boundary, and the moment you take the interior, those points gets removed. So the moment those points gets removed, you have a disconnected set. All right. So from here, uh, what you can say is that both of these statements are false because two, I have a very basic example, and the one you can always, so for one, what did we construct? We constructed a subset which was even path connected, but the interior is not even connected. Right? So hence both of these options are false, and that's the answer. Okay, so thank you for joining us, and we will meet again with another problem from TIF. And the college math courses admissions are open. You can take an admission. The ongoing course is real analysis.